Hello everyone. Let's start the class a little bit earlier. So today we will be talking about the solution of homework 4, which is about methods of proving. The first question defines something called the Fermat number. So Fermat number f of n is defined to be the integer 2 to the power 2 to the power n and then plus 1. Some examples are shown below. So when n is equal to 0, so f of 0 is equal to 2 to the power 2 to the power 0, so which is 2 to the power 1 plus 1, and it is equal to 3. And then f1 is equal to 5, f2 is equal to 17, f3 is equal to 257, f4 is equal to 65537. So actually, up to this point, all the numbers, all these Fermat numbers, they are all prime numbers. So long time ago, Fermat conjectures that, that all the numbers here are going to be primes. But unfortunately, f5 is actually not a prime number. So f5 is this very large number, and Euler is the first one who has shown that it can be factorized as a product of two primes. So in that case, f5 is not a prime. So, but then why are we studying Fermat number today? It is because Fermat number still is related to prime numbers. So the first question we want to show is some property about this Fermat number. We want to show that f of n can be computed by multiplying all the f values before it. So f0 multiplied with f1 multiplied with f2 up to fn minus 1. We get the product of these Fermat numbers and then plus 2. This will now become f of n. This one is very easily shown by using induction. We want to show that this is true for all n is greater than or equal to 1. So let's check about the case of f of 1. The value of f of 1, if you want to see this again, so it is equal to 5. And 5 is actually equal to 3 plus 2. And 3 plus 2, this 3 is equal to f0. So it is equal to f0 plus 2. So what does that mean? It means that the formula that we're seeing here, f of 1 is equal to f of 0. You don't have anything to multiply further because you multiply up to f of n minus 1. So f of 1, it turns out that it is equal to f of 0 plus 2. This formula works when n is equal to 1. Now, in general, we want to show that this formula works for every n. And using induction, we can do what? We can first assume that it is correct, the formula is correct for f of n. And we want to extend that, given this information, the formula is also correct for f of n plus 1. So this formula, we can assume that this is correct. And then what we want to investigate is the next case. So in the next case, the right-hand side will be f of 0 multiplied up to f of n. Is that okay? And then plus 2. And then based on this assumption, the product of this former part is simply f of n minus 2, right? So it's f of n minus 2. And f of n minus 2, this thing multiplied with f of n, it is f of n squared minus 2 times f of n. Is that okay? And this plus 2, we can make it into plus 1 and plus 1. The reason that I want to do so is this part we can do factorization. This part is actually f of n minus 1 square. Is that okay? This is f of n minus 1 square and then plus 1. Now, so what is f of n minus 1? Now, by definition, f of n is like this. So f of n minus 1 is 2 to the power 2 to the power n. So this part, we can replace it by 2 to the power 2 to the power n, the square of it, plus 1. The square of it is equal to 2 to the power 2 to the power n plus 2 to the power n in the index. There are 2 times, right? And then it is actually 2 to the power 2 to the power n plus 1, this term, plus 1. And this is f of n plus 1. So what do we know? So we know that if So if we assume if the formula is correct for f of n, then the formula will be correct for f of n plus 1. So finally, by the principle of mathematical induction, this is important, okay? What we have just shown is independently the base case is correct and also the inductive case is correct. These two, we still need to make a conclusion based on these two cases that they are true. So we can use the principle of mathematical induction to show that the formula is correct for all the cases. Okay. Now the next part is we want to show that any two Fermat number, they are relatively prime, which means that they don't have any common factor other than 1. We can show this, you can have different ways of showing this, but the easiest way I think is to show this by contradiction. So suppose for the sake of contradiction, there is a common factor d greater than 1 between the two numbers f of n and f of n plus k. Now from the result of A, we see that f of n plus k is equal to the product of f of 0 up to f of n plus k minus 1, right? And then plus 2. So in particular, this will be some integer multiplied with f of n and then plus 2. Now recall that d is a common factor of f of n plus k and f of n. So this means that this is a multiple of d, and this is a multiple of d. So if I put this to the left-hand side, we will see that 2 will be the difference of two multiples of d, which means that 2 will be a multiple of d as well. So d divides 2 properly. But we have the assumption that d is greater than 1, and then for a number greater than 1, and if it divides 2 properly, there is only one choice. D is equal to 2. Is that okay? But then, at this point, we have a contradiction, because we have assumed that d is the factor of f of n, but f of n is what? If we look at the definition again, f of n must be some even number plus 1. So f of n is an odd number. So we say that d divides f of n, but d is equal to 2, so it is impossible. At this point, we have a contradiction, and so this finishes the contradiction proof, and the overall thing, we are done. So what do we know now? So we can take this for granted. F of n and f of n plus k, they do not have common factor. For any two Fermat number, they don't have any common factor. Okay, immediately we can get the main result that we want to show here. We want to show that there are infinitely many primes. So how can we show? Yeah, because the number of Fermat number, there are infinite many of them, right? We plug in a new n, there will be a new Fermat number, right? And then what we know, if I pick one prime factor from each of these Fermat number, then these prime factors, they are all going to be different, because any two Fermat number, they don't have shared common factors. So if I pick a prime factor from f0, a prime factor for f of 1, and so on and so forth, we will have a lot of numbers generated one by one, and each of them are different from the others. So that means what? That means that we have infinitely many primes. Okay, so this is the end of question 1. Now question 2 talks about coloring of a grid. So in this problem, we have a 3 by 9 grid. So there's 1, 2, 3. One column has 3 grid points. We have 9 columns. Altogether, we have a 3 by 9 grid. And then we want to color the grid points here, each one of them either in red or white. We want to show that no matter how we color the grid points, we must be able to find a rectangle. For instance, this one, this one, this one, this is a big rectangle, right? And also maybe this one, this one, this one, this one. There are many rectangles here. It must be possible for us to find a certain rectangle such that all the vertices are colored in the same color. So in our example, if we focus on this rectangle A, B, C, D, yeah, this is a rectangle, right? The 4 corners of this rectangle, are colored in the same color. So this is what we want to show. Okay, so how do we show this? Notice that there are 9 columns, and then each of them, there are exactly 3 grid points. So because each of the grid points can be colored in either red or white, by simple counting, we see that there are 8 different possible ways to color a certain column. So ranging from white, 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 red, and then white, red, white, and so on and so forth, up to red, red, red. So there are 8 different ways of coloring a particular column. But now there are 9 columns. There are 9 columns, there are 8 ways only. That means that exactly 2 columns are colored in the same way. So in particular, for instance, let's see in this particular example, whether we can find 2 columns colored in the same way. Let's see. Yeah, there should be 2 columns. I do not find, so this column and then this column, right? So we have this column is white, red, white, and this column is also white, red, white. Is that okay? Now, if we focus on just these 2 columns, we will see that one of the color appears at least twice. In this case, this is white, red, white, so white appears twice. White appears twice. Now, if we focus on these 4 white vertices, they form the corners of a certain rectangle, and they are all in the same color. So the corresponding points form are the vertices of a desired rectangle. Okay? Yeah, form the corners. Okay, so there's some English mistake here. So, but I hope you understand what I'm saying. Now this is question 2, but we have a slightly more challenging part. So instead of having 3 by 9 grid, let's say we now only have 3 by 7 grid. So the grid is now smaller. And then again, we are going to color the grid points in red or white. And still, we want to show that there must be a rectangle such that all the vertices are colored in the same color. So how do we get that? So the proof is not difficult. We just need a slightly tighter analysis. So let's check the easiest case first. So suppose that some column among these 7 columns, suppose one of them has all points in red. Now then, what will happen? So there are several cases that we can consider. So the first case is if there is another column such that it has 2 or more red, then we are done. Yeah, because we can now find 4 red points such that they form the corners of a certain rectangle. On the other hand, if no other column has 2 or more red, that means that the remaining 6 columns, they must have, each one of them, they must have 2 or more whites. But then the cases with 2 or more whites, there are just 4 variations. So again, we have 6 columns, but then we can only have 4 types. So that means that we must have 2 types we must have 2 columns that are of the same type. And in such a case, then we can use the same argument as before, and then we can find vertices. This time, yeah, we can find vertices such that they are all colored in white here in this particular case, and then they form the corners of a certain rectangle. So this is the first case. When some column has all points in red, then we are done. Now another case is, by symmetry, if some column has all points in white, then we are also done. So the only remaining case that we need to consider is we don't have any column all in red, and we don't have any column all points in white. So what does that mean? So that means that out of these all the 7 columns, we cannot have all red, we cannot have all white. But then in that case, there are only 6 types of coloring that we can choose. Altogether 7 columns, 6 types. That means that some type will repeat, and then we're done. Okay, so this is the proof for the question number 2. Question number 3 is about a game called Magnus and Derek game. In this game, we have a table of n seats. So altogether, there are n positions around the table. At the beginning, let's say Magnus is at a certain location. Let's say Magnus stands here. What Magnus wants to do is Magnus wants to visit all the positions around the table. So Magnus will do what? Magnus will specify the number of seats that he wants to move around. But then he could not specify the direction. So it could be clockwise or it could be anti-clockwise. And Derek is the one who specifies the direction. Now the game here is Magnus wants to visit all the positions, but Derek wants to stop Magnus from doing so. So who will win this game? Okay, so every turn, Magnus specifies the number of seats that he wants to move around, and then after that, Derek will decide the direction. So for instance, let's say Magnus stays here and says 0, then Magnus will visit this position. And then let's say Magnus say 4. Then Derek decides whether Magnus should go in the clockwise or in the anti-clockwise direction. But 4 in this example here, it is the same, so Magnus will now move to this location. And perhaps at the next step, Magnus specifies 2. So Derek either specifies clockwise, so that Magnus will now move to this location, or anti-clockwise, so that Magnus will now move to this location. We want to show that when n is a power of 2, then Magnus can always succeed in visiting all the positions around the table. And then, this can be proved easily by induction. When n is equal to when n is equal to 1 or n is equal to 2, n is a 2 power, right? So when n is equal to 1 or 2, then we are done. N is equal to 1, then Magnus just says 0, then no matter what Derek do, Magnus will visit the position. And when it is 2, then it is also simple. Magnus can say 0, then Magnus visits the first position. And after that, Magnus says 1. Then no matter which direction Derek specifies, Magnus will move to the opposite side of the table and then visit that location. Now the inductive case is we want to show that suppose Magnus can always succeed when n is equal to 2 to the power k. And we want to show that Magnus can also succeed in the case where n is equal to 2 to the power k plus 1. So if Magnus can solve the case n is equal to 2, then he can solve the case n is equal to 4. And if he can solve the case n is equal to 4, then he can solve the case n is equal to 8, and so on and so forth. Now what we can do here is easy. Okay, so Magnus can actually use the strategy for n is equal to 2 to the power k to visit all the even numbered positions. So here, let's say this position is 0, 1, 2, 3, 4, 5, 6, 7, something like this. This is 0, right? So how can he visit this position 0, 2, 4, and 6? That's easy. Imagine that these 4 are gone. We know that there is a way that Magnus can visit all these 4 locations because it is from the inductive assumption, right? And when we have these seats filled in here, then Magnus can also visit these 4 locations, except that previously when he specifies moving 1 seat, then this time he should specify moving 2 seats. Previously, he mentions moving k seats, then this time we should move 2 times k seats, and so on and so forth. So that means that no matter what happens, there is a way that Magnus can visit all these even-numbered locations. And after that, no matter what happens, Magnus say 1. 1 means that we are now moving from an even-numbered position to an odd-number position. No matter what happens, Magnus will be in one of these locations, the odd-numbered position. And after that, we repeat step 1, doing the same thing, so that Magnus can visit all the odd-number positions. And that's it. So in that case, for this Magnus and Derek game, when n is equal to a 2 power, then Magnus can always win. But on the other hand, you can think about this at home. When n is not a 2 power, there is always a way for Derek to stop Magnus from visiting all the positions. And the number of positions that Derek can avoid Magnus from visiting is related to the smallest odd factor. The smallest odd factor of n. So if you are interested, you can think about it at home, and then you can actually search for the web for some description about this game. Why we call it Magnus and Derek? So Magnus comes from the word magnitude, specifying how far away that you want to move, the magnitude, and Derek corresponds to the direction. So Derek and direction, yeah, so specifies the direction that Magnus is going to move. Okay, question number 4. Question number 4 says that, let's say we have a path P with n vertices. We assume n is at least 2. We want to find the labeling, a certain labeling of the vertices, such that the labels must be chosen from 1 to n, and they have to be all distinct. So this is going to be a permutation of 1 to n. And then we want to have the absolute difference between the labels of adjacent vertices. They are all different. So what does that mean? So I have an example for you. Suppose that n is equal to 5. We have a path. This path has 5 vertices. Now, we are going to give a label to each of the vertex. And then, so this one is a 2, this one is 5, 1, 3, 4. And after this labeling, then we can check what are the difference between adjacent vertices. So this, the what? The difference is 3, 4, 2, and 1. 3, 4, 2, 1. They are all different. So we are done. So this is a labeling that is okay for this one. And in particular, we want to show that no matter what n we are talking about, there must be a certain label that satisfies these two constraints. Okay, this is an example of a proof by construction. So we don't need to count how many ways that we can do so. We just need to show there is a certain way that we can do so. It's relatively easy if you do some trial and error. So we simply label the vertices from left to right in the following way. We start from n and then 1, and then n minus 1, and then 2, and then n minus 2, and then 3, and then n minus 3, and then 4, and so on and so forth. We will see that we can now, based on n and 1, we get n minus 1, and then these two, n minus 2, n minus 3, n minus 4, and so on and so forth. So in the end, we can get all the numbers. So they are all distinct. Okay, question number 5. We are looking at a set X, where X contains the numbers of a specific form. So first of all, X contains the numbers that are real numbers between 0 and 1. And then for each of these numbers, the number of decimal places that it can have is equal to k, where k is certain natural number. So we have all the numbers from 0.1, 0.2 up to 0.99, and also 0.111213 up to 0.99, and so on and so forth. So we can have all the numbers of the form that are having exactly k decimal places, where k is some integer. Now notice that x is a subset of rational numbers, because each of the number x that we can see, for instance, let's say x is equal to 0.345, then this number can be expressed as 345 divided by 1000. So it is a rational number, right? So x actually itself contains the numbers, and each of them is a rational number. So it is a subset of the rational numbers. And because we know that the rational number set is a countable set, so x itself is also a countable set. But however, someone tries to prove that x is uncountable. So we have a proof, and this proof looks like the diagonal proof that we have explained in a class for showing that real number set is uncountable. So I believe you have already gone through this when you are working on the exercises. But if not, then yeah, you can pause this YouTube demonstration and then check carefully what it happens. So to quickly tell why it is not okay, so it is because there is something wrong with its proof. Which part is the error? So this is the error. So somehow In this proof, we construct a certain number x, and then we claim that this x is not listed by the correspondence using this method. So in that case, a contradiction occurs, and then we show that this cannot be a countable set, something like this. So basically, this proof is like this. We assume that x is countable, so there is a listing of the numbers in x with one correspondence with 1, 2, 3, and so on and so forth. And then we generate a certain number little x such that the first digit of x is not the same as the first number, the second digit of x is not the same as the second number, and so on and so forth. So in that case, we will see that this x will not be listed in the correspondence, but then this x looks like a number between 0 and 1 and should be in x. So in that case, we say a contradiction occurs. But then there's actually nothing wrong about this proof. The reason is that the constructed number x, it could have infinitely many decimal places. And if it is such a case, then it does not belong to the big set x. The reason is that the big X contains all the numbers that has finite number of decimal places. So in that case, X could have many decimal places and could be not belonging to X. So that means what? That means that it is perfectly okay that X is not listed. So if it is the case, then there is no contradiction. Okay, the original contradiction for proving the real number set is uncountable is we really generate some number that should be in the set, but then it is not listed. And in this example, in this question here, we generate a number which is not in the set. So it is perfectly okay that it is not listed. So no contradiction occurs. Okay, so that's all for the for what I want to show today. So let me double check if there are any questions. Okay, if not, then yeah, thank you. Let's end the class now. Thanks. Yeah, I hope that this time there won't be a lot of mistakes. So I want to apologize for the last tutorial where I have not enough time to prepare, so that it contains many mistakes. Yeah, I'm really sorry about that. Okay, that's all for today. And then next week, it is a reminder. Next week is going to be exam 2. And we will still have a lecture summary this Thursday. So Thursday is the lecture summary, and next Tuesday is exam 2. Okay, thank you very much. Okay, bye-bye.